Okay, so up until now we have been discussing common source amplifier and various aspects of it. So you must have noticed that we have been using something. We have been using a series combination of two sources in order to add the incremental output or incremental input to the bias, right? But why? What do I mean by that? So we wanted to bias the transistor. To bias the transistor, we needed a battery of value VGSQ, and also we wanted to apply the incremental small signal equivalent, and for that we needed to add another signal so that it adds to the voltage of the battery. And how can you add? You add two voltage sources in series, the voltage adds up, and that's what we essentially said that this is what our structure is. If this is Vi, this is VGSQ, this voltage will be VGSQ plus Vi. Okay. Now, while this works perfectly, there are some practical issues with it. What are those practical issues? One of the very most important practical issues is that you cannot, not often you can have access to two terminals of a battery, right? What I mean by that is, let's say you have uh, when you want to use typically when you're making an IC, when you're making a chip, right, you have one master power supply, and you have to derive all voltages, all subsequent voltages that are needed from that power supply. And typically that power supply is the highest power supply that is available anywhere, right? So now let's say you have this VDD corresponds to that power supply, right? Whatever, I mean 30 volt or 20 volt or whatever the power supply that you have, or maybe 5 volt. This VDD is the maximum power supply, but that is the only battery that you are allowed to have, right? So where from will you get this battery VGSQ, whose where you need access to both the terminals. One might say that I don't want to use this. I can as well say that instead of doing this, I will do this. I'll use a smaller battery and the voltage source in series, and this value of VGSQ I have derived from VDD, right? Fair enough. Fair enough argument to make, right? I have a VDD, I have a battery VDD, right? I put a resistor divider or something, and I reduce the value to the required VGSQ value, and that acts as the battery. And then I apply my input as I have shown here. The output of that, the terminal at the gate of the MOSFET will be VGSQ plus Vi, right? If you can do that, this will work. But there is another issue. The issue is, how would you get this Vi? Very often this Vi, you don't have access to both terminals of the signal source. One very common example is when, let's say, one stage is driving another stage, right? So let's say there is one stage, one amplifier stage whose output is this, and this output is reference to, let's say, V01 is reference to some ground, okay, and this is supposed to drive another amplifier stage which is also reference to this common ground, right? What I'm trying to point out here is that in the picture on the left, you are assuming that you have access to both the terminals 1 and 2 of the signal source, but in reality you probably have only access to terminal 1 because the other terminal is implicit ground, right? So the problem essentially is that we seldom have access to both nodes of the battery or even the signal source, right? So the problem is we seldom have access to both terminals of a signal source or a battery inside an IC, right? Which essentially means that even though you can put two batteries in series, in principle you can buy one battery from the market, you can get another battery from the market and put them in series, but you cannot do that in practice when you are building an IC, right? So implication is, consequence is, cannot put two signal sources or batteries in series. Note that this is a constraint in an integrated circuit environment, right? If you are getting batteries separately, right, this need not always be a constraint. However, if you are in the lab and you are using a signal source, you can see, if you have been in any analog circuit lab, you will see that signal sources are these big boxes, right, out of which two wires come out. One reference wire is almost always grounded, right? So even in an environment where you don't have to deal with the idiosyncrasies of an integrated circuit, it can become difficult to put a signal source and a battery in series, right? So the crux of the problem is that we cannot do this. If we cannot do this, what else can we do? So that will be the point of discussion in the rest of this lecture. Okay, so what's the issue? The issue is, I mean, to rephrase the issue, we want a scenario where we would want to have a signal source and a battery combination like this, where this has to be the MOSFET, right? And this I can assume to be ground because, I mean, the signal source is being driven by somebody where there is an implicit ground, right? So we want this combination, right? We want to get this combination, but the problem is that we cannot stack two signal source, one signal source and a battery like this, right? Now, in order to resolve this problem, we'll have to go back to the fundamental definition of a battery. So what is a battery? In principle, what is a battery? So a battery, right? So a battery is a source, or let me say an ideal battery. Ideal battery is a source of infinite charge, right? Why do I say so? Because I say that because if I put a current source in parallel with it, and I keep on drawing, what is the current source doing? The current source is drawing charges out of the battery, right? So even if I keep on drawing charges out of the battery for infinite amount of time, the battery will still hold a value of whatever it was supposed to hold, which essentially means that the voltage across the element hasn't really changed, even though you have been able, you were drawing, you have drawing charges out of it for indefinite amount of time, right? So in other words, I can say that it's an ocean of charges, right? It's a battery is an ocean of charges. Even if you take few buckets of water out of a ocean, the level of the ocean doesn't really change. Similarly, even if you take few coulombs of charge out of the battery, the voltage of the battery doesn't really change, right? So now, I mean, what is the equivalent analogy? What do you think among the elements that we know, right? Among the RLC elements that we know, which element corresponds closely to this behavior of a battery? You guessed it right. It's a capacitor, right? A capacitor an infinitely large capacitor is indistinguishable from an ideal battery, right? Right? Why do I say so? Let's say this is an infinitely large capacitor. Let's say I call it C infinity, and I have a voltage, let's say V bat across it. So what is the charge? The charge will be Q will be C infinity times V bat, right? And if I draw some charge out of it, right? If I draw some charge out of it, right? So let's say I draw delta Q charge out of it, correct? So what is the net charge? What is the net charge after I drew delta Q charge out of it? The net charge will be Q minus delta Q, right? So after I drew delta Q charge out of this battery, what will be the voltage across the battery? The voltage across, this is V nu, will be the charge divided by C infinity, correct? So I get Q by C infinity minus delta Q by C infinity. What is Q by C infinity? Q by C infinity was V bat minus delta Q by C infinity. What is delta Q by C infinity under the assumption that C infinity is infinitely large? This. So limiting value of delta Q by C infinity tends to infinity is 0. So this goes to 0, which means V nu is equal to V bat, right? So in other words, an infinitely large capacitor is indistinguishable from a battery. Now you might turn around and say, from where will I get an infinitely large capacitor? I agree, that's a problem. We'll address that somewhere down the line. But for the time being, let's assume that it's a large enough capacitor, right? It's a large enough capacitor which is able to, which probably will be able to act like a battery, right? What is large enough? We'll define later. But let's assume that we have taken one step forward in replacing a battery, right? So if we agree with this, right? If we agree with this, what is the solution? The solution is, I have a voltage source EI, and I wanted to have a battery, right? I wanted to have a battery having VGQ, but I can't have a battery. What is the alternative? The alternative is replace the battery with a C infinity capacitor, right? But what is the charge across this capacitor? If we don't do anything, the charge across the capacitor will be 0, right? Which means we'll have to somehow charge the capacitor to the value of EGQ, right? So how do I charge a capacitor? One way to charge the capacitor is to say, hey, so let me do this. Let me apply a battery here of value VGQ. If I do this, right, what will be the charge? What will be the charge across C infinity? Assume for the time being that Vi is equal to 0, right? If Vi is equal to 0, what do you think will be the voltage across C infinity? The voltage across C infinity will be VGQ, right? Right? If Vi is equal to 0. Now, so this is VGQ if Vi is equal to 0. But does this solve the problem? Now let's assume Vi is not 0. Now let's assume Vi is not 0. If Vi swings, what happens to this gate voltage? The gate voltage, as you can see, doesn't change. Why? Because it is connected directly to the battery VGQ. Correct? So this gate voltage is connected to a battery VGQ. Whatever happens to the rest of the world, the voltage at the gate of your MOSFET will not change. Correct? So that's a problem, isn't it? So what's the solution? So to understand this, let's try to figure out what is the root cause of the problem. So let me get rid of the MOSFET for the time being, and let's concentrate what is happening. Okay. So the problem here is when the input is swinging, right? When the Vi is swinging, this voltage is stuck at VGQ, right? And where is this incremental current that will appear due to this Vi? Where will it go? The incremental current, however large it might be, will go into this battery, right? And because the battery gives you no impedance, right? Battery is essentially an ideal short, right? If you use superposition, what will you do? We'll essentially say that VGQ is an ideal short. Because it is an ideal short, the current that is flowing out of Vi is not able to change this voltage Vg, right? Since this voltage, we are not able to affect this voltage Vg simply because VGQ is an ideal short. This is causing a problem. Correct? So what is the solution? We cannot have an ideal short, but we also want the voltage Vg across the capacitor, right? So if we now divide this problem into two different sub problems, right? And we say that while Vi is a sinusoid, right? This battery here is a DC, right? Vi is getting applied at frequency omega naught. However, the battery VGQ is at a frequency 0, right? Okay. So what is the impedance offered by the capacitor? What is the impedance offered by the capacitor at frequency 0? So at omega equal to 0, i.e. for VGQ for the battery, VGQ, C infinity offers infinite impedance. Why? Because the impedance offered by a capacitor is 1 by omega times infinity. If omega tends to 0 or omega is exactly equal to 0, then the then the I forgot to put the j, then the uh, mod of zc is essentially infinity, right? Okay. So what is the moral of the story then? The moral of the story is that the capacitor is giving you infinite impedance to VGQ, right? Now, what impedance does C infinity offer to Vi? So, since Zc is 1 over j omega C infinity, so if omega is equal to 0, Zc is equal to infinity, right? If omega is equal to omega naught, what is Zc? Zc is equal to 1 by j omega C infinity. And under the condition that C infinity tends to infinity, what do I get? This offers 0 impedance, right? So in other words, C infinity acts as a short circuit for omega. Correct? So let me highlight this because these are vital conclusions. And it should not surprise us that C infinity is acting like a short circuit for omega naught, because what was C infinity replacing? C infinity was replacing a battery, right? And a battery, what is the incremental equivalent of a battery? The incremental equivalent of a battery is of an ideal battery is a short circuit, right? It should not be surprising that C infinity acts as a short circuit at omega naught. However, a battery also gives 0 impedance at DC. However, a capacitor doesn't. So that's the key difference between a battery and a capacitor, right? So which a capacitor is a frequency selective circuit, a frequency selective element, which essentially means that at 0 frequency, it gives you infinite impedance. So now, can we leverage this? Can we leverage this and and see if something can be done?